loud, I think, is last time. Okay, so for those who are watching this recording, welcome to our Zoom session. This is the review for exam 5. So we're going to do chapters 12 and 13. So at first I was doing notes on paper because I feel like my carbon chains look nicer that way. And I switched to my iPad, so the first like little bit of notes, just like 1.5 pages on the iPad. So let's go ahead and go through this. So when we're talking about the structure and properties of alcohol, we know that alcohols are just, am I going to upload it? Oh, actually, let me, I can send the link in the chat. I have to email it to myself. I sent it in the, what is it called? The group me though. If you are in the group me, then that is where that was sent. Okay, are you in the group me? Because I'm not sure if I'm going to be able to send it in the chat. If somebody can send the link to the notes in the chat, that would be great. I would really appreciate that. Moving on, let's just do this for so that we're not too short on time. But like we were saying, alcohols are just compounds with an OH, also called a hydroxyl group, on an sp3 carbon. This is important, just because I remember Dr. Dowdy stressed it when I was in the class, so I feel like that would be an important thing to know. We know that alcohols, which is a whole compound, they have a hydrophobic region, which is going to be that part with a carbon chain. So that's like that part over there. And then they have a hydrophilic region, and this is going to be that part over there. We know that something that is soluble is when there's like a certain amount of something that will dissolve in water at room temperature. And then, for example, butanol is a soluble compound. We know that the shorter the carbon chain, then the more miscible it's going to be. So it's going to be a little bit easier to dissolve, just because that OH is really what's giving it its hydrophilic properties. But anyways, that's not really too important for your exam. Thank you so much for sending that. Over here, then we have compounds with OH have a high boiling point because of hydrogen bonding. This is kind of the important part. I definitely see Dr. Dowdy asking you guys a question like rank in order of increasing, what is it called? Boiling point or melting point, freezing point. You can really do it in a couple of ways. Let me try. This is a link to the group me, I think. So if you like download it and then email it to yourself, then download it to a computer, then I think that would be able to work. So do any of you guys have the notes? Because they are like kind of important. Okay, let me stop sharing my screen really quick, and then I will put in a Google Drive for myself. And then I will download it from there. Oops. I think hopefully this works. Okay, perfect. And it is a PDF. Okay, that's fantastic. It worked. Okay, awesome. That is so fantastic. Okay, so we can get back into what we were doing then. So let's go ahead and share the screen. I also love for anybody watching the recording, you're probably very annoyed at this point. But yes, over here, Dr. Daddy definitely can ask a ranking question, and I definitely think that he would do something like that, just because this whole thing is about alcohols, and it just raises the boiling point. Anyways, so when we're doing the nomenclature, this is pretty easy. It's kind of just the same thing that we've been doing. And then alcohols like always have the highest priority, even when there's like pi bonds and stuff like that. It's going to have the highest priority. And then we see that when we have something like this, which is a benzene ring with an OH on it, this is a phenol. So then we get into phenols a lot later in the chapter. And then over here, we can see that even when we have an OH and this nitrile group and then this chlorine, that the OH has the highest priority even over this chlorine over there. And we would number it as 1, 2, 3, and then 4, like that. Cool, any questions? Okay, awesome. So over here, when we're talking about the acidity of phenols and alcohols, this is another thing that Dr. Daddy can definitely talk about. And it's like really easy to ask a question like that. When we have our OH and then when it's deprotonated, it becomes an alkoxide, which is just a compound that has an oxygen with a minus sign on it, because you know that oxygen likes to be bonded to two things and have two lone pairs. But when it gets deprotonated, ends up having 3 lone pairs. So then we look at this, or we have increasing stability, and then we can see that like a carbon chain would be the least stable, and then nitrogen, and then oxygen, and then a halogen. And that's again something that we've been talking about like all semester long, is electronegativity. And we know that like more electronegative things can hold electrons better. So then we can see the increasing stability with that lone pair on there. And then over here, we have increasing acidity, and that would kind of be in the same pattern. And then we know that something is acidic if it's able to donate a hydrogen group or if it's able to accept an electron group. But a lot of the stuff that we're talking about here in this chapter is definitely just like donating a hydrogen group. And if you can really understand the way that like electrons will be localized in order to keep that hydrogen happy, and if it's not happy, then it will just leave, then the more readily available it is to leave, then the more acidic the compound is. So like over here, let's say that we had something like chlorine bonded to hydrogen, and then we have something like this like carbon chain bonded to this oxygen. This chlorine would be able to really like grab all of those electrons from this bond, and it would have like a really big partial negative, and then that would have a big partial positive. Whereas this oxygen, yeah, it's able to pull the electrons from that bond from the hydrogen, but also there's carbons here that are like donating electrons as well. So this is going to be less partially negative compared to the other chlorine and hydrogen like that. So yeah, that's pretty much that. We can ask ourselves the question, what are the factors that affect acidity of phenols and alcohols? One of them is resonance. So we can see that, especially for phenols, they're like super, they're much more stable compared to just like a regular cyclohexane, because these electrons are conjugated. So you're able to like move them around and make a lot of different resonance structures, and that really like stabilizes that charge. And if it's able to like keep that electron, so like over here, this would be talking about acids in the way where we're accepting electrons, not donating hydrogen. So you kind of have to remember that can go both ways. But yeah, resonance is really important for acidity. Then we have an example of this. We've done this question before in our review, but now it's actually making sense, hopefully. But we have which alkene reacts faster with HBr. So we have just this one pylon right there, or we have these two benzene rings, and we can see that with the conjugation, if the HBr were to come into any of these and then create our carbocation intermediate, then it would be more stabilized in B, because the other electrons would be able to like move towards it and then still stabilize one another. So I think that's super fun and exciting. Another thing that affects acidity is induction. So we have oxygen is pretty electronegative, so it has other surrounding elements that donate their electrons, making the hydrogen on the OH not as needed. So then this is exactly what I was saying earlier, as the acidity increases, that can correlate to the willingness to donate a hydrogen. So over here, we have just like a regular OH, and that pK is going to be 16. It's 16 to 18. But over here, when we have all of these chlorines that are able to donate their electrons, because we know that these chlorines all have 3 lone pairs on each of them, and although they're really electronegative, that oxygen is still like, hey, like I want some of these electrons. You guys have a ton over there, like share a little. And then this hydrogen would like pretty readily just like something could just like easily come and like nab it off from there. And then oxygen would be happy with all of those electrons. So that's what's making it acidic. And then the last thing is solvation, which is the amount of solvent that can like kind of surround your solute. So over here, again, we have this just OH on there, and that pK is going to be 16. Whereas over here, when we have tert butoxide, we can see that because it's bulky, not as much solvent would be able to surround it and like get into all of those nooks and crannies. So it's going to be less acidic. So I made a couple of connections between this. So we have the more stable the conjugate base, the more acidic that it's going to be, the compound. And then we have that OH makes things soluble. So the more accessible that the OH is, the better the acid it is as well. Especially because we know that we need this OH in order to be solvated in something like water. So then over here, we have preparation of alcohols via substitution or addition. And actually, this is where we have notes from now, I'm pretty sure. I don't have notes for the other page, but we have notes for this up there, so we'll do that in a second. But over here, let's talk about the preparation of alcohols via reduction. We know that there are different oxidation states for elements, but carbon kind of gets its oxidation state based off of other elements that it's connected to. So in this case, we can have oxygen, we can have carbon at like -4, -2, 0, +2, and +4. And pretty much reduction is just a decrease in oxidation state. But another way you can think about it is reduction is a gain of hydrogens. And you guys also were talking about oxidation in class, and yeah, oxidation is loss of hydrogen, but oxidation from now on is also going to be gain of bonds towards like an oxygen atom. So that's, who would have thought? I don't think Dr. Dottie would ask you guys to calculate the oxidation state at all. Maybe he would have like a couple of different examples though, and ask like, oh, which of these is it, of these compounds is being reduced, or which of these is being oxidized. Definitely something that he would ask. So yes, moving on. Now this is exactly where we were before pretty much, but we have deprotonating alcohols, which we didn't really look at this earlier, but we have a couple ways to deprotonate alcohol, which is what we were talking about earlier with acidities and stuff like that. You can do it with a strong base like NaH, and then we can see that this hydrogen becomes like a hydride and then grabs that hydrogen on that OH, leaving it like this. And then we can also do metals. There wasn't really like arrows in your book, so I didn't really pay too much attention on how that actually happens. I will say though that maybe half of the H2 that could be important, maybe, who knows. And then over here, we have the preparation of alcohols. This is where we left off just now. We have a couple of different types of reactions. The first type are substitution reactions. Here we can have, it depends on how substituted our carbon is. So like over here, if we have a primary carbon with this chlorine on there, then that's going to be an SN2, and we're going to use a strong nucleophile. Again, this is that SN1, SN2, E1, E2 stuff that like you really just wish you didn't have to worry about anymore, but here it is in this chapter. The mechanism of this one, when we have a strong base, the first thing that I like to do whenever I see anything that has sodium on it is I like to draw it separately and then have like whatever it was connected to with a minus sign. So let's say that we had something like NaOMe, and then that Me is just methyl. The first thing I would do is draw it like this. So over here, that's kind of the same thing that we're doing, but we have this hydrogen that has both of the electrons on it. And this can kind of like represent a lot of other things that we see, just as long as we have that H minus. But it comes in, grabs the hydrogen. Is this the one that you were talking about? Oh, okay, my bad. Okay, yeah, so do SN2 reactions happen in one step or in two steps? Yep, so they're going to happen in one step. So pretty much what would happen is we have our chlorine over here, and then our OH looks like this with a minus sign. This OH is going to come over there and grab and attack that carbon, but now the carbon would technically be attached to 5 things because we have that hydrogen over there. So then that chlorine is going to leave. So we have nucleophilic attack and loss of leaving group all in one step, giving us our final product. How pretty. Awesome. Over here, we have our tertiary carbon, and when we have that, then we know that we need an SN1 reaction, and we can also tell based off of our nucleophile. So over here, we have a weak nucleophile, and this would happen in 2 steps. But we know that the rate would only be determined by one thing, which is what that one is standing for. Another type of reaction, another type of reaction that we do with alcohols are addition reactions. So we know that addition reactions happen when we start with a double bond. And all of these reactions we've gone over before. Not in the last exam, but I think the exam before that, because I don't think I did a review for the last exam, but I definitely went over this for you guys. But anyways, yeah, so this is pretty much what they look like. Pretty. Remember that hydroboration oxidation is anti-Markovnikov, which means that the H is going to go onto the more substituted carbon, and then OH is going to be on the less substituted carbon. Any questions on those 2 things?
Just to like make sure, for SN1 and SN2, we just have, I think you already said it, but just wanted to make sure, because I always like forget. SN1, look at if it's like tertiary and just kind of like go as normal. SN2's primary, go as normal, but it's like 1 step, just to make sure. I always forget for some reason.
Yeah, so SN2 is going to happen in 2 steps, and SN1 is going to happen in 2 steps, and SN2 is going to happen in 1 step. The way that I remember it is you just have that number there, and then like the opposite is going to be the number of steps that you have. And then you're going to have that 2 represents how many things the rate is determined by. So like rate equals K times, and then in this example, it would be this.
Okay. All right, that makes sense. It's just like
Okay.
the little things, but I'm good.
Yeah, it's okay. I also don't think it'll be like too important. Definitely later when we are talking about which ones form racemic mixtures, that's when it's going to be important, but we'll talk about that in like 5 minutes. So over here, before we can really like even actually start to react our alcohols, we have to prepare them sometimes, or sometimes we're given just like a ketone and we want to react something that we need an alcohol for. So we're able to convert those things. So a couple different ways, there are a couple different ways to do it. One of them is reduction, which means that we're going to be losing bonds to our oxygen and gaining bonds to hydrogen. So over here, this is an example of a reduction because we lost one of the double bonds to our oxygen, and then, oh my bad. I'm in the library, so there's just like literally an announcement that goes off every single hour. I had an interview and I was like in the library all day and I didn't have time to like go home or like do it anywhere else. So I literally did it in the library, and in the middle of my interview, the announcement went off. It was the most embarrassing thing that's ever happened to me. So yes, wear a mask. You're actually supposed to wear a mask in the study room, even if you're studying alone. But I was like, I'm gonna post on my YouTube channel. I'm not gonna wear a mask because I'll look ugly. Okay. They're literally fine. That's why you wear a mask. You're gonna give yourself COVID. I'm vaccinated. Anyways, you're not. No, they'll literally shoot you if you have 2 people in a study room, bro. Anyways, moving on, we have, again, reducing agents. They're so beautiful. Love them. One of my favorites, H2PD. You guys just remember this reagent, live by it, eat it, breathe it, sleep it. Because if any of you guys are going to be studying for the MCAT, sometimes there are questions about reducing agents. This one right here. And this one is so fun because she's such a strong reducing agent, and we'll see that in a second what they do. It's absolutely insane. But moving on from the alkene hydrogenation by metal catalysts, we have sodium borohydride. Let me see if I have the mechanisms for these. No, I don't have the mechanisms for these yet, but we have a couple mechanisms for other things in a second I will get to. Over here, we have sodium, let me move this over actually. Sodium borohydride, and you can react it with a lot of other little reagents down there to make soluble and stuff like that. Again, same reaction though, we're making the same product, but with this one, we have a racemic mixture, and same product because there's no crazy things. Well, we'll see in a second how they sometimes form different things. But yeah, sodium borohydride does the same thing, gets rid of that double bond and makes it an OH, just like that. And then also watch out for racemic mixtures because this is going to be an SN1 reaction. And we know that in SN1 reactions, we form a trigonal planar, which is like sp2, and sometimes sp2 is trigonal planar. And that means that it's going to be flat. So the OH could come, or sorry, it wouldn't even be the OH. It would be what is coming to attack. No, it is trigonal planar because it's sp2 right there. Yeah. So when you have that hydrogen come in and attack, it can come from this side or from this side, which gives us either a wedge or a dash. So we're making our beautiful enantiomer racemic mixture. And we do have the mechanism for this in case you guys were curious. I know sometimes I get curious about the mechanisms and it keeps me up at night, really. So I didn't want that to happen to you guys. So look how pretty. Wow. Any questions? Perfect. Okay, so moving on, we have lithium aluminum hydride, which I know here I have that it's a strong reducing agent, and I was mulling it over as to whether lithium aluminum hydride is a strong reducing agent, because it's like strong, but it's not like as strong as other things. So I'm actually starting to question myself as to whether it's a strong reducing agent or not. I do know, however, that it is stronger and more reactive than our sodium borohydride that we just saw. Amazing. So over here, it's going to again do that same thing where we just have our OH. But this is also reacting with ketones or aldehydes. So yes, these are our examples. Let's actually look at the mechanism for this one. How fun. Pretty much the same thing is happening. Nice. And then we have a reduction of an ester, but we'll do that in a second. That's like my favorite reaction, which I say that about a lot of reagents. They're just so exciting. Anyways, so over here we have the NADH4. But look at this. We have a cyclo pentane over here, and we can see that there's a pi bond. Amazing, interesting. And we see with the sodium borohydride that it's just taking that double bond, coming in, doing its business, and making an OH. Same thing with the lithium aluminum hydride. But then with our H2 and metal catalysts, they really just have sticky fingers and they're getting into all of the different carbons. They just cannot control themselves and they steal that pi bond, leaving our cyclopentene into a pentane. Oh, can you guys believe it? I'm shocked, truly. Did you guys go over naming for aldehydes and ketones? I feel like I did not see that in the book this past chapter. Okay. Also, I'm pretty sure I learned it when I was in Orgo 1, but that's just me. I also learned IR and NMR, which you guys don't seem to be learning this at all. And I'm honestly shocked because when I took the class, I was studying for the finals for like 3 weeks. Like literally I had like a schedule and every single day I was sitting down for like 4 or 5 hours and taking notes and doing practice problems and stuff like that. And I remember thinking to myself, like, I'm not even going to learn that material. And I'm telling you, like 20% of the finals was literally just NMR and IR. And we had just learned it in class like the day before. Anyway, moving on from my grievances. I'm so glad that you guys are not learning that though. You guys will have to know it for Orgo too in the lab. So, yes, no, you won't feel, but like, look really quick. Look how cute my study schedule is. This is what I always do before finals. I have like my life stuff, meetings that I have over here, school stuff, MCAT stuff. I definitely recommend making a list like that. If you guys have any study questions, I would consider myself a study expert at this point in my life. So over here, we have lithium aluminum hydride is more reactive than sodium borohydride. And something so fun is that lithium aluminum hydride will reduce carboxylic acids and esters, but sodium borohydride will not. So this is just like such a fun reaction, especially for the ester one. So I hope you guys are ready to see what happens and how we are going to react this. So when we have the carboxylic acid, pretty much what happens is, we'll look at carboxylic acid in a second. But over here, same thing that we saw earlier, but once that oxygen goes up, instead of just being reduced and grabbing on a hydrogen, it actually reforms the double bond and gives us our nice little carbonyl group. And then, so like the ester is gone, oxygen has left the chat. And then the lithium aluminum hydride comes again, which is why I'm pretty sure you have to put excess LiAlH4 when you're doing something like this, comes in, and then we're left pretty much, this part over here is exactly what we're seeing over here, except this is for sure an aldehyde, but this could be an aldehyde or a ketone. How nice. Just so exciting. One of my favorite reactions ever. And so, yes, yeah, there you go, excess LiAlH4. And again, make sure that if it is a chiral center, that you are making that nice little race mixture and putting dash and wedges. Any questions on that? Carboxylic acid, you guys did not need to know the mechanism, but I'm pretty sure it's the same thing as esters.
So when it says like excess for like the lithium aluminum hydride thing, it's still making an alcohol, but it just has two hydrogens attached to it instead of like one, then, since it happens twice. Or maybe I'm just getting.
Yeah, so there's like no hydrogens. I'm sorry, I'm like trying to think. Okay, so there are no hydrogens there, and the reason that we do excess is because we want 2 new hydrogens on that carbon. Is that what your question was?
Yeah, so if it didn't have like the excess in front, would it just have like one hydrogen attached?
If it did not have excess, then we would only have gone through half of it. So we would be left with, this would have a minus sign on it. And then we would have a hydrogen like this.
Right, okay.
And yeah, so instead of having an oxygen again, we would be left with this. So an aldehyde instead of that alcohol, because that other LiAlH4 would come and finally give us this. But if it was only one, that was actually a really great question, then we're left with an aldehyde.
Okay.
Will you send the mechanism notes on grouping? Yeah, so if you scroll all the way down here, we have the mechanisms. But I put them all in one. Yeah, no problem. Okay, yeah, really great question. I like that question a lot. So yeah, that's all we have. Then now we have preparation of, where is it? Okay, of diols, which is pretty much just a compound of 2 hydroxyl groups. There's a couple ways that we can do it. Again, these are all just the ones that we just saw. Also, especially for the extra credit questions, if you have to put in any sort of lithium aluminum hydride, make sure you number it, or else Dr. Guy will mark it wrong. So keep that in mind. Okay, we have dihydroxylation of alkene, and then you have thinner antidiols. You guys know this one, super easy. We've already even gone over epoxide openings, I think. I don't know why you guys knew this reagent, but it was in the extra credit questions, so you guys have gone over this reagent for sure, somehow. Did you guys go over this reagent? Like with the mechanisms and stuff? Yeah, so it's just, you know, same old, same old. You guys already know this. Easy peasy. How fun. Okay, so just for reference, we have I'm not even sure what the word names are called, but we have RCO3H gives us anti-dihydroxylation, and OSO4 with NMO gives us syn dihydroxylation. Then here we have the preparation of alcohol via Grignard's reagent. Did you guys go over Grignard's reagent before as well? I'm trying to see how in depth we should be going. So I have a no and a yes, I think. Not until, okay, just that chapter. Okay, perfect. This one, so fun. All of Orgo 2, you're going to be just building chains with Grignard's reagent. It's really just the most amazing thing you'll ever see in your whole life. Pretty much what happens is that this is an example of what the reagent will actually look like. It'll have like this nice carbon chain and then MgBr. So sometimes when we just have something like this with a halogen, then the magnesium will come in and like attach itself like that. This is another example, pretty simple for both of these. But what's really interesting is that we're able to take something like a ketone and make it into a alcohol and a CH3 all at the same time. So there's a couple of different things that will react with this. First, we have the ketone. Again, that's how it will react. We have aldehydes, and that'll leave us with a CH3 from our Grignard's reagent. You can see that that's in red. And then our OH from this oxygen being reduced. And then remember, racemic mixtures, I didn't actually write out the racemic mixture, but you can use your imagination. I said racemic. And then we have esters. This is going to react pretty similar to how we had our excess LiAlH4, where it reacted 2 times, which is why we need excess here, where it comes in, and then we're left with that CH3 on there. And then the lone pairs are on the oxygen. It comes back down. The oxygen, like ester part, leaves. We have another CH3 come in, and that's why we have 2 CH3s. But let's go ahead and look at the mechanism for this, because this one actually is pretty important. So this is the reagent and how it reacts with ketones and aldehydes. We only see it once, but again, you guys know how I like to write out my sodium separately with like the Na+. I'm doing the same thing here for my Grignard's reagent, where I have my magnesium chloride. I think that's what that would be called, with a plus sign on it, and then I put the minus sign on my carbon over here. Oh my gosh, actually, I put too many carbons. Okay, that's what the final thing would look like. Remember, also, that was really great of me that I made that mistake, because I don't want you guys to make that mistake. Count your carbons. So over here we have 1, 2 carbons, so we should only have 1, 2 carbons, like that. Okay, actually, then this was correct. Yes, 1, 2 carbons. How pretty. Are you guys kidding me? I love this reagent. Anyways, moving on. Oh yeah, this is what I'm talking about with the esters. Adorable. I think it's really nice, the fact that last time in office hours, I was still confused between esters and ethers. None of you guys should be confused. This is an ester. We'll go over ethers in a little. Here, CH3, goes up, comes back down, double bond, attacks it again, racemic mixture, protonated oxygen. Awesome? Very, very awesome. SOCl2 and alcohol. Okay, that one is not that important right now. So now we have our Grignard's reagent, and so something that you guys, I even put on there. I said I'm almost 99% sure you'll get a question like this on your exam, where it's carboxylic acid reacting with Grignard's reagent. Please don't touch the double bond. It's just going to go ahead and grab that hydrogen. Sometimes, but we will see something in a second about how to both protect. We're going to go over in a second, but this is if we have our Grignard's reagent reacting with something else. But when we're reacting, or just also keep this in mind, when we have our Grignard's reagent, which is why I kind of like pointed that out over here, that this is what it looks like, reacting with the with something that has a carboxylic acid, then that is how it's going to react. It's just going to deprotonate it. Yeah, so in the book, it said that it's not going to react in a way that, oh my gosh, it's not going to react like how the ester and ketone and aldehyde are reacting. It's just going to go in and protonate it, or sorry, deprotonate it. It isn't, because if you protect the alcohol, then the reaction can occur. Yes, but it deprotonates the OH though. That is the reaction that happens. It just doesn't turn the entire thing into an OH and get rid of the double bond. Cool? And now we're going to go ahead and move into the protection of alcohol. And first of all, I'm pretty sure that when I learned this, the girl next to me was cheating on my exam. So I'm traumatized still. This is in person too. I'm telling you, her eyes were like literally looking at my paper. But anyways, yes, here we have the protection of alcohols. I think that it's just such a fun reaction. And is there another reagent that you guys learned where the alcohol group does this or something like that, and the protecting group looks like that? Or is that Orgo 2? Orgo 1, yeah, I'm not remembering what this is called at the moment. Is it Apostolate Chloride? Interesting. Okay. I do think that I have it PSCl later, maybe. I actually don't think I have it, but that's another protecting group, and it looks so pretty. So, anyways, here we have protecting groups. It solves that issue that we were having earlier about how Grignard's reagent isn't able to make its reagent with something that already has an alcohol group on it. So pretty much what happens is that this is what putting a protecting group on it looks like. Trimethyl sulfide. Okay. I personally use trimethyl ether as this which is this OTMS. But yeah, I'm pretty sure that Apostolate Chloride, and I think that's pyridine, I think it's pyridine. Pyrimidine, what is that? I don't know. So that's like DNA or something. Anyways, this is what the reaction is going to look like. Here, we just put our protecting group on it. It was super easy, just reacting it with OTMS. That magnesium is going to come on, and then we have that MGBR like that. And then what happens is that the MGBR breaks off like that, and then the lone pairs over here come and attack the thing that we are reacting with, leaving us with this beautiful, amazing structure. It's going to go ahead and protonate itself. And then in order to remove our protecting group, we use TBAF. Don't remember what that is, but you know what? I can't even think. Anyways, that's just what the removing group is, period. Okay, because I said so. Now we have two alcohol groups. And this is a diol. How pretty. Any questions? I'm going to look at the Apostolate Chloride really quick. Let me I think you do. It's just so pretty, but it does the same thing that we just went over, but I'm trying to see if it has a different removing group. If anybody is aware of that as a fact, that would be really nice if you could share with us.
I thought the Apostolate Chloride was not for like protecting the OH. I thought it was for like the reaction where you have like alcohol and you want to convert it into like a chloride.
I'm also looking at that right now. It's SN2.
Yeah, like you would just have
So
a chlorine attack, then it removes that as a leaving group.
I'm gonna be honest. The only protection group that you guys have in your book seems to be this TMSCl, EP3N, which
Yeah,
that
it's
literally sounds like a foreign language.
I think it's like TBAF, and then there's another one too that you can use. I think it's like I forgot. There's like something that's really simple that you could also use instead of TBAF. It's like a fluoride ion or something.
Book is saying, yeah, it can be removed with H3O. Oh my gosh, I'm literally blind. Can you guys see that? Okay, yeah, you can. You guys just gotta read, okay? Protecting groups TMSCl with EP3N. That's another. That is how you get the protecting group on there. Nice. Pretty? I agree. And then the removing group is going to be TBAF. Period. Okay, cool. Any questions? Concerns? Comments? Questions? Awesome. So here we have the preparation of phenols. How beautiful and nice. I don't think you're going to actually have to know. I don't want to say you don't have to know it, so I drew it. Okay, nice. That's all we have to know. Here we have the reactions of, because remember, Dr. Dowdy has limited questions that he can ask you. I doubt he's going to ask. Men one. I feel like every single time I tell you guys, like, oh, I don't think he's going to ask that, then I'm like, if he does, then they're going to be so upset. So actually, just look at it for a little longer. And then while I talk about this SN1 reaction. Over here, we have a 3, which is tertiary, what is that? Alcohol will undergo an SN1 reaction when treated with hydrogen halide, which is, just, there we have HBr, because hydrogen is the H, and then the halide is like Cl. Bromine halide? I don't remember. Okay, that's not even important. It is, apparently. Oh my gosh. I'm sorry, you guys. Okay, bromine is a halide. Moving on. Here, that is hydrogen halide. I'm not even going to question myself anymore because I was smarter 4 hours ago when I did this. Anyways, that is how it's going to react. SN1 is a substitution. Pretty. SN2 with OH, this is where it gets interesting. We have primary and secondary alcohols undergo SN2 when treated with, again, that's a hydrogen halide, sulfur oxide, chlorine, SOCl2 is what we're going to be calling it, and PBr3. Or when it is converted to tophlate, this is what we were talking about with the the TSCl. Over here, we have primary oxygen alcohol, primary alcohol with HBr. Nice. And then we have, that would react as HBr, like just alone. But when we have HCl, we also need to react it with zinc chloride, zinc dichloride. I don't know how to name that actually. So we're just going to call it ZnCl2. Because OH is not a good enough nucleophile to grab that hydrogen from the chlorine, because we know that chlorine is really likes those electrons. But they're reacting pretty much the same way. Just one of them is adding a Br and one of them is adding a Cl. And then we have the other type of reaction is when we have OH and then we have our tosylate gets added on, because the tosylate makes it a good leaving group. And then the halogen is able to react. Again, we have the inversion of configuration because of that SN2. And then also because we have that intermediate. So it can, look at this really quick. That's going to be a hydrogen. Yeah, so pretty much what would happen is that leaving group leaves, and then we're left with a carbocation intermediate in this one. So it's flat. And we're attacking it at the other side. Questions on that? Awesome. And then we have our primary alcohol, again, reacting with SOCl2 and PBr3. And that is that not what I literally just drew over there? Why did I draw this twice? Is there something else I wanted to say? I don't think there's anything else I wanted to say. I just wanted to draw it because it was pretty. Anyways, so we also have elimination reactions for alcohols. Reactions keep on coming. Here we have tertiary alcohol undergoes E2 when treated with H2SO4. I'm gonna stop looking at the mechanisms, but if you guys want to scroll down, they're there. This is more reactions. Again, that nice little tosylate, OH must first be converted to tosylate or an alkyl halide in order to react as an E2. Over here, I was wondering for a second how we have a tertiary, but I don't question things. I just follow the rules. I don't make them. Over here, we have reactions of alcohols, and then now we're going over oxidation, which is when we have more bonds to oxygen, less bonds to hydrogen. How many times can a primary alcohol undergo oxidation? Twice, and we can see that here. The first time it's turning into an aldehyde, second time it's turning into a carboxylic acid, depending on what it's reacting with, like actually. And then over here, we have our secondary alcohol, and that's just going to turn into a ketone. And then tertiary alcohols don't get to react because they are connected to too many things. Over here, we have chromic acid is an oxidizing agent. And that is, the first step is to actually make the chromic acid, and there are two different ways to do it. And then we just react it with water, and then it makes it just, it's such a fun reaction actually, if you guys want to scroll down and look at it. And now these are, I feel like this was so pretty the way that I set them up side by side. We have primary alcohol with PCC gives us an aldehyde. Secondary alcohol with PCC gives us a ketone, okay? Secondary alcohol with chromic acid gives us a ketone, okay? Primary alcohol with Thorne oxidation, which is DMSO-COCl2, and then that ethyl, what is that, like triethyl nitrogen, gives us an aldehyde. And then we have secondary alcohol with Thorne oxidation gives us a ketone. Is anybody just picking up a pattern here? Kind of. And this is one mechanism, as annoying as they are to look at, they're really important just because you can actually see what's happening. And even just like the most basic aspect of it, when we have our OH like this, and then let's see, let's go look at the mechanisms. which I know I said I wasn't going to do, but honestly, I feel like whenever I say I'm not going to do something, it makes me want to do it. So I'm never allowed to make decisions ever. Over here, the sworn oxidation, it looks really complicated, so I actually feel like that's a bad example to give. So let's look at the ester reaction again with Grignard's reagent. We can see the way that, I guess we're going backwards, so we actually can't look at that one. Let's look at SOCl2. And that is not the same reaction either. Okay, we're gonna have to look at it looks messy now that I'm looking at it, so I feel kind of bad that I said that it was an easy reaction. But pretty much what's happening, first couple stages, we're just making our chromic acid. This is what I was saying, how there's two different ways to make the chromic acid. We can use chromium trioxide and then also sodium dichromate. But look at those arrows, just so thoughtfully made, where this oxygen comes in, grabs that hydrogen over there, and then this bond comes and makes a double bond, leaving us with the, I think this is acetone, and then that chromium, I'm not sure what this would be called, leftovers, they leave. But I just think that is just so beautiful. And now I don't think Dr. Dowdy would test on that mechanism though, because it is a little hard. But just you can see how things are happening. Fun. But yeah, I'm not sure. Let me see before I make this claim. It looks like every single time a primary alcohol is reacting just one time, you're going to end up with an aldehyde. That is my final statement. Is that, can anybody confirm that?
Wait,
or deny?
Could you repeat what you said? Because I was just zoning off for like 5 minutes.
Primary, I'm so glad that you guys are zoning out. Primary alcohols will always form an aldehyde when they are being oxidized.
No, there's one that doesn't.
Okay, except for one.
Yeah, except for the one. But everything else, yeah, it goes to aldehyde if it's primary.
So when in doubt, if you have a primary alcohol, just choose the aldehyde. If you have a secondary alcohol, choose the ketone. When in doubt, worst comes to worst, but hopefully that doesn't happen. Anyway, oxidation, this is literally what I had in the book, and I'm like, okay, and what about it? There we have it. That's it. Let's go ahead and take a moment to appreciate this beautiful, beautiful cursor handwriting I did. Amazing, impeccable. Over here, chapter 13, my brain actually turned off when I did this, so it's like we're looking at it for the first time together. Over here we have introduction to ethers. That's what an ether looks like. Nomenclature, there's a couple different ways to do it. There's the IUPAC and then the systematic name, and I'm pretty sure that Dr. Dowdy he might ask for maybe both. I don't know. The IUPAC naming for ethers is weird in my opinion. I feel like the systematic name makes a lot more sense, but I'm gonna be okay. Also, Bailey, I know what you're about to say. I thought that IUPAC name and the systematic, I'm pretty sure this is what the book said though. I'm like 99% sure that the book had exactly like that. And I was just like, so do I not know what an IUPAC is? I just, am I dumb? I had to ask myself that question today. I ask myself that question very often, actually. Okay, all of a sudden, 13.2 just ceased to exist. so short. Yeah, in the book, it says a systematic name is constructed by choosing the larger group to be the parent alkane and the smaller group as an alkoxy substituent. And then it names it like that. So don't shoot the messenger, because this is simply what the book said. But I know I did not do it like this when we did the worksheet. But anyways, we're just gonna forget about it. He's not gonna ask for both. So just know, okay? It's just, you just look at it and you're just supposed to know. That's how I personally do IUPAC names now. That's how I do any sort of nomenclature. You just look at it and you're like, oh, that's ethyl methyl ether, easy. Yeah, maybe, do you guys think that we found a typo in the book? Do you think that I am dumb and not able to interpret books, perhaps? I think it's just new. Okay, let's just look at the IUPAC then, okay? And if he asks for the systematic name, then that will suck, okay? Moving on though. We have structure and properties of ethers. Ethers with low molecular weight have low boiling points, and ethers with a big molecular weight have big boiling points due to London dispersion. You're really just you just like use 3 brain cells, this will make sense. It's like if you are multiplying, if you are like boiling a lot of things, then it will take longer, is the way that I'm understanding that. But also, do I even have 3 brain cells? Another question I ask myself every day. Crown ethers, these so beautiful. I don't know how Dr. Dowdy would ask you guys a question on this, but I will look for you guys because I have a couple of questions for us to do, which we should have done 10 minutes ago. But I will stay 10 extra minutes for this reason. Okay, we have preparation of ethers. What a nice, beautiful mechanism that is. We have acid catalyzed dehydration of ethanol, Esters reaction. We get that protonated hydrogen, nice. Protonated oxygen, water leaves. The other thing attacks it all at the same time, leaving us with this beautiful, nice ether. But that hydrogen is really just ruining the scene for us. He can ask which crown ethers solvates what. He could, but again, he has like 25, what is it called? Questions to ask you guys things. So the chances that he is going to do that. I think he has asked a crown ether question before. I'm gonna look in my class notes for you guys in a sec, and I will find them because I know I've seen a crown ether before in my lifetime. That hydrogen, again, it's just ruining the scene for us. So it comes in and grabs it. Perfect, ether, easy. And then we have the Williamson ether synthesis. That is what is happening. That is what it looks like. Pretty much we are making an ether. Who would have thought that ether synthesis results in the creation of an ether? I would have never. Then we have the oxymercuration, demercuration, which I did not even highlight the whole thing. That's kind of ugly of me. And we have the Markovnikov addition of OR, which is just oxygen and like a carbon chain or a hydrogen. And I'm pretty sure it's carbon chain, and a hydrogen across a double bond. This is Markovnikov, easy, easy. Yep, perfect. Any questions? Awesome. So then we have reactions of ethers. We have acidic cleavage. That is what it looks like. We have auto-oxidation. That is what it looks like. I don't even remember seeing a lot of mechanisms, to be honest, in chapter 13, just like words. And then we have nomenclature of epoxides. Epoxides are just oxygens in a circle chain thing, not a circle, like a closed unit that has a name, cyclo. And then we have the oxirane is the one that we are really going to focus on here. And we have substituted oxiranes are called epoxides. Amazing, beautiful. This is naming for it. I'm pretty sure that Dr. Dowdy wants this one, and I know that because he told us that. But there are unfortunately two ways to, my iPad frozen on the screen.
For naming it, I was like struggling with that part of the chapter right now.
It's okay, we can do this naming question really quick. Over here, we have this side is going to be methyl. This side is going to be ethyl. And so we go to this one first, like 1 and then 2, because E comes before M. This is something that you guys probably remember because you guys are really smart, but something that I didn't even remember. You would like to practice one that is racemic. Okay, we can do that. But when I did this example, I was like, this is so interesting. I feel like maybe, who knows, the methyl could go first. How am I supposed to know? E comes before M. You gotta go, when you're going like numbering, alphabet, crazy. Over here, these are gonna be, oh, I already wrote ethyl. But there's like 2 of those ethyls. So then we have 2,2 diethyl, which is this part over there. And then we have 3,3 dimethyl. Okay, that's that part over there. And then we have oxirane. How pretty. Pretty cute, I know. That the other way to name it, I think that Dr. Dowdy would mark it wrong. So I would play it safe, and just because I know that I've heard him say that's how he wants it named, to just name it that way. Awesome, fantastic. And then we have preparation of epoxides. We prepare with peroxy acid, and there are 2 types of peroxy acids that your book mentioned, and they are MCPBA and peroxy acetic acid. That is what they look like, and pretty much they form that epoxide, which you guys already know this. I know you guys already know this because you guys told me that you did. And then pay attention to cis and trans. If it looks like this, then it's going to be cis, and if it looks like this, it's going to be trans. This is like kind of like the E and Z thing, but it's not. So yeah, just keep that in mind, guys. You guys are doing a great job. Here we have the preparation from halohydrin, which is when we have like a halogen and hydration. So then we have like that addition reaction, Br2 water, enantiomer. Bam. We have, when we're going backwards, we use NaOH. Nice. Here we have the ring opening reactions of epoxides. I think epoxides are so fun and exciting. Reactions of epoxides, strong nucleophile. There you go, open. Regioselectivity, nucleophile attacks the less substituted or less hindered carbons, or so we think. There, bam, opens. And then we have stereochemistry. When the carbon attacks, it has inversion if it's chiral. Awesome. Acid catalyzed ring opening. This is where it gets interesting. When we have acid catalyzed ring opening, there are a lot of things that can open rings, by the way. That was in the book. There were like 8 of them. Like CN was one of them, C111N. Something weird though, when we have a secondary or sorry, yeah, a secondary carbon compared to a primary carbon, then we're going to have our acid catalyzedness attack at the primary. But when we have primary and tertiary, it attacks at the tertiary. And the book said the word steric like 600 times. And I honestly, I don't even know what it was telling me still. So we'll see if we even have to know that when we go over examples in a second. But yeah, this is, I'm not sure what that even is telling me. But I wrote it down for you guys. So that was nice. Examples. Ta-da. Okay, that's so nice. We're looking. Did I copy this down incorrectly? I'm trying to ask myself if this is supposed to be here or not, but I don't remember. I feel like it's not. I'm going to go ahead and say that it's not supposed to be there, and it's just going to attack that side, because then we have it's adding on there, so it's not. Okay, awesome, perfect. And then we have, when we have a secondary and a tertiary carbon, it attacks the tertiary. Pretty. And then we have phenols and sulfides. I'm pretty sure all you guys had to know was like a couple simple things in phenols. When we have it being added on, for some reason the E is kept. When phenol is a substituent, it's called mercapto, which I feel like that's so fun. It's like my cat though, her cat though, mercapto. And then over here we have a substitution, so just NaSH. That is going to flip the stereochemistry. I'm assuming that it's happening in a one reaction, and that is Y. And then over here, we form disulfides with NaOH, H2O, Br2. Bam, disulfide bonds. In class, he called it like sulfile. The book just said mercapto, so if I don't think that he would call it something weird. I think it would just be called mercapto then. Sulfile is interchangeable. Okay, and that's perfect. Slash sulfile. Sulfil. I can't even read. So then we learned all of these reactions and also how to undo them. So here, in order to break a disulfide bond, and disulfide bonds are important for what, you guys? This is like a biology question. Stuff. Perfect. Thank you guys so much. It's okay. You guys don't have to. I don't want to overwhelm your guys' brains. But if you guys come to me at the end of the semester, I'll tell you guys. But in order to break them, HCl and zinc, who would have thought? Beautiful. And then here we have sulfides, which is kind of like ethers, but they're sulfides. And then we have diethyl sulfides, and then we have methyl thio. When it's a, or just, it would be thio, and then whatever is also connected to it when it's a substituent. When you're making a thiol into a sulfide, you use NaOH and a halogen on the thing. It's kind of like when we're adding on to triple bonds, but except you use NaNH too when you do triple bonds, so it's not actually. And then we're done. Oh my gosh. What is mercapto? That is for SH, which is thiol, but when it's a substituent, so it's not on the parent chain. And then we number it like this. 1, 2, and 3. Okay, perfect. So I am going to open. Okay, it's not going to be one. I'm imagining though that when I did this, it was a mix of your exam 1 and exam 2. So we're going to go through here and just see what we would even need to know. This is an E2 reaction question. Wouldn't need to know that. Bromination. We also need to know that. Which of the following is the correct mechanism for the elimination? Okay, this is an E2 reaction again. E2 transformation. You wouldn't need to know that for this exam. Proper product. Would you guys need to know this for this exam? And this kind of looks like epoxide opening. Okay, so let's do this question. What is the product of the following reaction? So over here, what is happening is that we have CH3O and A. Again, I told you guys that when I have my sodium on there, I like to just immediately like rip it off, put a plus sign on there, and then the oxygen has a negative charge. Then with those lone pairs on the oxygen, it's going to come in, and is it going to attack the more substituted or less substituted carbon? Do you guys think? Yeah, so it's going to go ahead and attack the less substituted carbon. And then what happens is that right there, where the lone pairs are going to the oxygen, that is where the oxygen gets put in. And then, so nothing is going to happen to, I can't use my pen, so this is like actually a little bit annoying. Can I use my pen? I don't think so. It's okay. But you see that other carbon that isn't being attacked, that's going to stay the same. We don't want to bother it. We're not a H2 with metal, and we don't have sticky fingers. So we're just going to deal with the carbon that we're looking at. And that is, however, going to flip its stereospecific specificity. So we're going from cis to trans in this nice example. And then that is what the final product is. Cool. Any questions on this one? Okay, awesome. Let's go ahead and look at the next question, which is the following alkenes carbocation arrangement. Okay, this one, I definitely see you guys getting a question like this. Rank the following compounds from lowest to highest boiling point based on your knowledge of intermolecular forces. So we know that something with, or let me ask you guys this question. What would make something's boiling point high?
Hydrogen bonding.
Hydrogen bonding, and then what elements do hydrogen bonding? Yeah, oxygen, fluorine, and nitrogen. So over here, let's go ahead, and since it wants from the lowest to highest, the lowest one is going to be something that has absolutely nothing that can hydrogen bond. It's kind of just a big carbon chain, and it's just literally like taking up space, not doing a lot for us. But it's something like cholesterol. It has a nice long carbon chain, stabilizing your cellular membrane. But yeah, long carbon chain. Over there we have 2, and that's going to have a really low boiling point compared to something that would have oxygen on there. So then moving on, the next thing is going to be 5, because although it is there's an oxygen on there, it's not actually hydrogen bonded to anything. Like, it can hydrogen bond to something, but at that very moment, it's not. So that one is going to have the next boiling point. And then after that, we have 3, because that one only has 1 oxygen, it just has 1 alcohol on there. The other part is still making it a little bit unstable. And then from there, we have 4. And I feel like that 3 and 4 can be a little bit tricky. But we have 4 because that oxygen, again, it can hydrogen bond. It has like the opportunity, if it were given the opportunity, then it could hydrogen bond. Probably wouldn't be super happy hydrogen bonding, just because, what is it called? Then the oxygen would have a plus sign on it, but it could. So the more oxygens, the better. And then finally, we have 1. It's going to have a really nice high boiling point because of the way that those 2 alcohols are on there. Yeah, perfect, Bailey. We have 2, 5, 3, 4, and then 1. Perfect. That was a great question. That is mechanism question. This looks like it is a naming question over here, the one that on the bottom. So we have some, I feel like Dr. Dowdy really likes isopropyl, and I've told you guys this before. Can you guys corroborate that? No, it's okay. I'm glad that you answered it. Oh my gosh. Here, 1 second. Okay, I am back. Okay, so yeah, I feel like Dr. Dowdy likes isopropyl. We have an isopropyl here. Sometimes you just gotta take a step back and just look, and you can see the isopropyl. And then we have 1, 2, 3. 3, we have our alcohol. We know that we're gonna go that way anyways, because the other way would give us like super weird substituents. Am I right? And then we have 1, 2, 3, 4 isopropyl, 4 ene as well, but that's going to be N because we take the E away. And then we have what are those called? Carbons in total, which is oct. And then we're going to do E and Z because we have that, but I feel like Dr. Dowdy would probably do something where you're having to do R and S. So we'll look at the one right below that and then see that R and S. But yeah, the final answer there would be E4 isopropyl oct 4N3O. Awesome. Next, we have draw the skeletal structure of the following compounds. We have 2-ethoxypropane. I got that incorrect on my exam. I remember when I did not know how to name or draw ethoxypropane, and I drew like the ugliest thing in the whole world. Okay, wait, now that I'm looking at it, I'm starting to second guess myself, but who am I to, what in the world? 2-ethoxypropane. Ethyl prop, that's going to be 4. 3, 4. I thought, what? But why is it right? So who wants to explain this to me?
I just look at like the little bottom thing, like looks like the birds that you draw. And then so the oxygen is attached to the second one, and then it has an ethyl attached to the oxygen. So the bottom one is propane, and then it's on 2, and then it's ethoxy because it has an ethyl attached.
Okay. That is very, very true. But why did I draw my propane like that is what I'm trying to understand. Why did I not just make it a 3-carbon chain? But instead it is a
Well, isn't
looks like
three
a,
carbons?
it looks like there's a methyl because there is
I think that's just the oxygen connected to the propane.
ooh, that is so true. Oh my gosh. Did you guys just open your eyes and see it? Oh my god. No, literally, I have not eaten since like 5 in the morning. So everybody can just ignore me for the rest of the day. But you just have to look. Are you guys like, you just have to like see it. And then that's the answer. That is how you do it. There's no further explanation for anybody because you just have to open your eyes. Anyways, moving on. R5 Bromo. He wouldn't have a question like this, I don't think. Let me think, would he? He might. So let's go ahead and look at this one. We have 1, 2, 3, ol. We know that, again, oxygen is going to have that really nice high priority. We also see that there's a methyl on here. Going up, we have then 4 carbons, 5 carbons, and 6 carbons. We have our hexane that we have, and then 5 bromo, because 1 down is 5, and then 5 methyl as well. And then doing that 1, 2, and 3, oxygen is going to be 1. That carbon up there is going to be 2. The carbon to the left is going to be 3. And then that other methyl is going to be 4. So then if we were going this way, going this way, that is an S. Why did I? Okay, so you're just gonna put that oxygen on a dash. That is how we can, or we can like flip it. Draw it the other way. You know what I mean? Just draw the enantiomer. Just flip it over, because that is actually an S. That was wrong. This is just incorrect. Moving on though. I don't know what I was even thinking when I drew that. Here we have skeletal structure of the alkyl halide that forms, okay, that's not on this chapter. Also not on this chapter. Also not on this chapter. Actually, this one. No, H2O, H2O4, that's old stuff. Okay, provide the structure of the major organic product of each of the following. Here we have, yep, this is all stuff that you guys would need to know. We have BH3, THF, H2O2OH, and what is something interesting that we know about this reagent? Anybody know something interesting about this reagent? So fun. It's literally written on the paper. If anybody just wants to, okay, yeah, perfect. Thank you so much, William. It is going to be anti-Merkavnikov. Thank you, Bailey. Yes, my favorite. And so then we have the hydrogen is going to add to the more substituted, and then OH is going to be added to the less substituted side. And we did not have the mechanism for that, but we had it in the past. So you guys are just super smart and know that. Then over here, we are looking at this substitution reaction with PBr3. And what kind of reaction are we having here? like what is happening. This is going to be a substitution. Is this SN1 or SN2? Just considering the fact that we have a racemic mixture, which means that we had an intermediate. So yeah, means that we had 2 steps, and that's going to be SN1. Thank you guys so much. We just went ahead and did this exact question on the review. Draw the major organic product and detailed stepwise mechanism. That's just H2SO4. You guys, I'm not sure if you guys would have to know H2SO4 again, but I feel like you wouldn't. So yeah, that is those questions. And then we have more, so do not fret. I have plenty more questions. Okay, that is medium infrared stuff, that's NMR stuff. Okay, which of the bases below would not be strong enough to determine? Okay, we have done that before. You guys did ketoenol. Okay, question 4, a prominent, oh no, never mind. You guys wouldn't need to know that either. But I remember that was such a fun question to do for myself. Which of the, okay. You guys wouldn't need to know that either. Classify the following. Okay, there you go. This is a kind of oxidation reduction question that Dr. Dowdy would ask. We have, this is my favorite way also to break it down. We have oxidation is gaining carbon halogen bonds and losing, and then that X is like oxygen, it's chlorine, yep, and then losing CH bonds. Whereas reduction is losing those carbon oxygen bonds and then gaining carbon hydrogen bonds. So over here, if we're looking at number 1, in the first one, we have C6H10, and then we are given after that C6, that should be H11, but I don't know the alphabet, H11 chlorine. So because of the fact that we not only gained a CH, but we also gained a carbon halogen bond, this is going to be neither. How fun. Definitely something Dr. Dowdy would ask. This next one for 2, we have C5H8O, and then we are then given C5H8O2. So one more oxygen is going to be oxidation. We have C5H4O4, and then we are given C5H6O4. So we have 2 more hydrogen bonds, and that is going to be a reduction. Does that make sense for everybody? Is everybody seeing how I did that? Okay, perfect. I would definitely be prepared for something like that. Let's see. Okay, what is the product of the following? This is the perfect, literally the perfect question. Over here, we have something with 2 alcohols and PCC and CH2Cl2. And so on that first alcohol, we have a primary alcohol, and we know that when PCC reacts with a primary alcohol, that gives us an aldehyde. And then when PCC is reacting with a secondary alcohol, that is going to give us a ketone. So if we look at the options here, first one is giving us 2 ketones, that's no good. Second one is giving us a carboxylic acid. Oh my gosh, they reacted it so much that would be like, what would that be? I definitely know that there's a way to get to carboxylic acid. You have to reduce it again with something that I have no thoughts left to think, but it's in the review. And then over here, question number 3, we have an aldehyde and a ketone. That looks really good. But let's go ahead and look at number 4 really quick just to see what went wrong there. And over there, we're only reacting with that secondary alcohol. So that one is a no-go. This one is definitely something Dr. Dowdy would ask a similar question to. Cool? This is how I would expect the questions to look tomorrow. Awesome. Very nice and cool. And then we have that just like chromium CrCO3, which is a strong oxidizing agent, which is what gives us the carboxylic acid, right straight from primary, which is what we were talking about earlier. So not all primary alcohols go straight to aldehydes because we have that nice, beautiful reagent to show us that. Moving on. What is the correct classification? Okay, this is, again, a really nice one of the following reaction. So it looks like we're turning a ketone into a ester. Yes? So if we were looking at that, we have C3O, and then we are then becoming C3H6O2. So what happens is that even just looking at it from a basic standpoint, we have a new carbon-oxygen bond. We went from a carbon-carbon bond to a carbon-oxygen bond. So what kind of reaction is this? Elimination reactions are when the degree of substitution increases. Substitution reactions are when there's displacement of an atom with another atom. So we're literally just getting rid of it and not adding anything else. We're just substituting like that little bit. Reduction reactions are when we decrease the degree of oxidation. So for example, when a carbonyl becomes a carboxylic, carbonyl becomes like an alcohol. But over here, we do have an oxidation reaction because we are clearly adding on another carbon. Yes, so this is not a substitution reaction because that's not how substitution reactions happen. It's just not. In substitution reactions, you just like attack that carbon and then it leaves. But like there wasn't really leaving. Here, I guess there was, but no, they just shifted over. So everything was the same. We added, making this an oxidation reaction. Cool. Perfect. Which of the following compound that matches the IR? You guys don't need to know IR. Okay, that is another IR question. Provide the major product of the following reaction. This is such a fun one. We have OSO4, Na2SO3, H2O, which is just NaO and NMO, yeah. And that is going to add it in syn or anti, you guys. Yep, we have syn addition here. I'm not sure if you guys would have to know terminal alkynes reacting with BH3 again, but just in case, you might need to know it as like an intermediate step or something, where like the aldehyde is getting, you guys might see like aldehyde turning into alcohol or something like that from a terminal alkyne, and just know, I feel like you might need to know it, so know that terminal alkynes with BH3, THF, H2O2, H2O, will give you a beautiful aldehyde. Cool, you guys? Awesome. Okay. Draw the structures of the missing compound intermediates. So over here, I'm assuming that you're given the final product, and then you're having to move backwards. So that is not even something that you would need to know for this exam, really. Propose a mechanism. Okay, that was just adding on, which is such a fun thing to do, really. Okay, that one is again IR. What alkene yields the following? Okay, that's O3, ozone. I feel like you guys don't need to know ozone. Iupactane, not gonna need to know that one. I think these are pretty much all of the questions that I have. Does anybody have something specific that they would want to go over? Any specific questions you guys were like really wanting to go over, and perhaps with examples would be good? Well, we're here. Let me. Where did I take this class? Such a long time ago. I'm like 50% sure that I have something here with the crown ethers. I do have a question that is related to the homework, but I can alternate. Okay. We can go over the homework question, but let me try and find that crown ether question really quick, because it's really actually just going to bother me now, knowing that I don't know, that I know I've seen a crown ether before from the lecture. Did you? Here it is. How did I find that? How did I even find that? Oh my gosh, that is insane. Here, the things that I have written is that they look like crowns, have oxygen, are cyclic compounds. From inside they are polar, important for substitution reactions. In substitution, we need oxygen polar solvents. That is all I have written about them. But how did I even find it? Seriously, that is impressive. I impress myself every day. Okay, so that is pretty much it then, I guess. Let's go ahead and open reagents. And let's see the question. Okay, so that is gonna be, I guess I'll end the recording here. If you guys have any questions and you're watching the recording, feel free to message me. Like, comment, and subscribe.